Oh, g'day there, Year 13 Physics. Thought I'd bring you guys outside today for a little look at collisions, a reminder of what collisions look like in Year 12. So, we bang some balls together, check this out. It's a linear collision, one dimension, because the balls can only move back and forward in that one dimension, and we know that we're going to use momentum to solve that kind of problem. Let's have a go at using momentum to solve a problem like that. Okay, so here's a classic momentum problem for you. Initially, quite windy. We got the black ball rolling in, mass of 0.5, speed of 1.2 meters per second, collides with the blue one, mass of 0.4, not moving. That's what our initial conditions are. Afterwards, we know that the black ball reduces in speed down to 0.5 meters per second, but same direction. What does the blue ball do? That's your challenge. I want you to find out how fast the blue ball is moving. And tell me if this is an elastic collision or an inelastic collision. Okay, so the first step, we've got a couple of equations we've got to remind ourselves of. We've got momentum is equal to mass times velocity. P equals mv. Mass in kilograms, velocity in meters per second, momentum, kilogram meters per second. And conservation of momentum. We know that the final momentum is going to be equal to the initial momentum, so long as no net force is act. And we can calculate that out for the initial conditions. Look, we've got the initial momentum as the black one plus the blue one, mass times velocity, 0.5 times 1.2 plus 0.4 times 0. And so we end up with an initial momentum of 0.6 kilogram meters per second to the right. So what do? We start by knowing that the total momentum afterwards must be the same as the total momentum before, 0.6. And we calculate up how much momentum that black ball is still carrying. P is equal to mv, 0.5 kilograms times 0.5 meters per second, 0.25 kilogram meters per second. Well, we've got to use vectors to make sure we get this exactly right. Check it out. Total momentum, 0.6. That's the red arrow going to the right. We know that the black one's still carrying 0.25 to the right. That's the black arrow, 0.25. And we know that the black one and the blue one have to add up to the total. So how much must the blue one be? It needs to be the difference from 0.25 up to 0.6. 0.35 is how much the blue one carries. So we can use our momentum equation now to work out just how fast that blue one's going. V is P over M. 0.35 over 0.4, 0.875 meters per second. Now, have you worked out if that collision is elastic or inelastic? If you haven't, you better do it. Remember, elastic collisions means kinetic energy is conserved, stays the same before and after the collision. Inelastic means it changes. Work it out. Oh, maybe you didn't remember the equation. EK equals half mv squared, where that m's the mass, v's the speed, and EK's the kinetic energy in joules. Now pause the video and work it out. So for that first one, you should have done half mv squared, half of 0.5 times 1.2 squared. Hopefully you came out with 0.36 joules as your initial kinetic energy. Don't need to worry about the blue one, it's not moving. so no kinetic energy. So we work it out for each of those two balls individually, the black one and then the blue one. The black one, half mv squared, half of 0.5, of 0.5 of 0.5, half of a half of a half of a half is around about 0.06 joules, and the blue one, half of 0.4 times 0.875 squared gives you around about 0.15. So thinking grand totals, 0.06 and 0.15, EK total 0.21. We started off up here with 0.36. We've ended up with 0.21. That's inelastic. That means that some of that energy has been transformed into heat, sound, that kind of thing. We've lost energy from the system. So, just to finish off for today, a whole different way of thinking about this is talking about velocity of centre of mass, which is an idea that comes along after calculating the centre of mass of a system. And so if we think about during a collision, we've got these two balls and they both stop. We know that the centre of mass of the two balls is roughly halfway between them. And if this ball advances, the centre of mass still roughly halfway between them, and now the centre of mass is exactly between them. And then if this one stops, this one keeps moving, centre of mass is there and there. And so what we see is that in explosions and collisions, the centre of mass moves at a constant speed, and that works not just in this one-dimensional kind of example, but it also works in two dimensions. We can calculate the speed of the centre of mass by going m1v1, the momentum of the first mass, plus m2v2, momentum, you could think about it as being momentum of the second mass, plus as many different masses as you like, divided by the total mass gives you the speed of the centre of mass. And that speed stays the same in explosions and collisions. Check it out. Keeps moving along at a constant speed.